All right, everybody, hello and welcome back. Today we're going to talk about how we can use technology to create models for both exponential and logarithmic data. So if we take a look back at what we did yesterday, we wrote the equations of exponential functions when we were given 2 points. Now, that works great when we know that they perfectly fit an exponential function. However, when we are dealing with real life data, it doesn't always fit perfectly. So instead, we can have calculators do the equation writing for us. Now, what we're going to want to do is we're going to want to first determine if we are writing an exponential or log regression. Now, regression basically just means it's like a best fit from your calculator. We are creating an equation based on the data that we were provided as best as possible. So typically our problems will tell you whether we want them to be exponential or log. So what we're going to do is we're going to take our table of values, such as this one, and we are going to first plug in our table values into a calculator. We could use Desmos, we could use our calculator. For our purposes, I'm going to be using Desmos. The next thing you're going to want to do is notice that the headers of your table are going to be the X1 column and the Y1 column. So what we're going to do is we are going to write in a separate line underneath there, y1 tilde a times b to the x1 power. What this is this is the instructions for our calculator to go ahead and take the values from our x1 column and our y1 column and create an exponential equation. Below that, it says write the exponential regression equation inputting the parameters a and b. What that means is our calculator is then going to give us a and b values that we are then going to use to write our equation, which will be our regression model. So let's take a look at this first example. It says, given the data, write an exponential regression model, then predict the number of visitors. So I don't know exactly what this is to, but this is a number of visitors to a specific place after the year 1990. So 0 years is 1990, 4 years after would be 1994, 1998, and so on. What we are going to do is first plug in our values into our calculator. So I already did this just to save a little bit of time, but if we are interested, all we have to do is click in a new line, click our plus in the top corner, and we can create a table. Now, I already have my values in here, so if we click on the little plus magnifying glass down here, it will show us our data. As we can see, the values kind of increase from left to right, but it's not exactly a straight line. It is going to be a regression for an exponential function. What we want to do then is we are going to want to type in our equation y1 tilde a times b to the x1 power. The last thing we want is to go ahead and click our log mode button. I know we are writing an exponential regression, but that log mode button is essentially just going to standardize our process, so it's something we want to keep included. Therefore, you can see that it gives us a and b values. So our equation is going to be y equals 163. Let's round to 2 decimal places just for a standard practice. 73 times our b value, which is 1 point, I think it was 0.8, yep, to the x power. So this is the exponential equation that our calculator created based off of the information we were given. Now what we can do is we can use it to make predictions. So what we're going to do is we are going to try to predict the number of visitors that we will have in 2022 based on the data we are given. That's why we're using the equation that our calculator came up with. Now 2022 is going to be 32 years after 1990. So it would be like if we had a 32 added onto our table. So what I'm going to do is use that equation. Except I'm now going to plug in an x value of 32. This will tell me my y value, or number of visitors expected or predicted based on our model. So if I flip back to our calculator, now I have my values down here, but what I can do is See if I can add an extra line somewhere. Guess we'll be going right there. What I can do is I can go ahead and type in my calculator. We have 163.73 times 1.08 to the 32nd power, and that gives us 1,921.71. Now, since we're talking about visitors, obviously we can't have 0.71 of a visitor, but since 0.71 tells us that we are going to be rounding up, our prediction is 1,922 visitors. And that's how we use our exponential regression. Now, the one other thing I want to point out here is we have an R value, which is our correlation coefficient. So if I go back up, to expedite this process in Desmos, what we can do is we can click on what looks like a couple points and then a line in between in the top left corner right by the number 1. If I click it, it will actually calculate whatever regression I would like. So I'm doing the exponential regression. I'm going to click log mode. There is my equation. So this is what we're going to be doing, but if you notice they give us an R squared value in this case. The R squared value is 0.97. Because our R squared value is 0.97, is very close to 1. And what that means is our data fits the line that our calculator created, which is right here, very well. The closer it is to 1, means the better fit it is going to be. All right, so it's essentially the extent of these problems. We've got a similar example right here that says, given the data, write an exponential regression model, then predict the number of bald eagles in Paris in 2023. So again, we have years after 1963, 0, 11, 18, and so on. And then we have the number of bald eagle pairs. Maybe that's what this word should be, pairs instead of Paris. So same idea, we're going to take our table and we are going to plug it into Desmos. If we go back over, I actually already did that, again, to save time. What I'm going to do is I'm going to unclick the top table and I'm going to click our second table. Now, the reason I did that is because we are now plotting different points. So I want to show these data values instead. I click the little plus, and as we can see, there is our data that seems to follow an exponential curve. Now, here is the difference. Again, we could press that button that is right next to our 2 that will calculate the regression for us. However, what I want to show you is our equation for the regression is going to be a little bit different for this problem. And the only reason that is because if you look at our table, we start with the x2 values and the y2 values. So my equation is going to be y2 tilde a times b to the x2 power. Again, the equation is essentially the same. I'm just saying get your values from the x2 column and the y2 column. So we've got an a value of 397.53. Our b value is 1.08 once again. To the x power. Now, this one is a little bit different. It's a coincidence that our b value has to be the same value, that we're again getting about 1.08. It could be anything as long as that base value is positive. So here we can see we've got our r squared value of 0.9827, again, very close to 1. And if you look at the graph, that should make sense. It looks like our values are very close to the line, which means our model is a really good fit. When we type in the equation ourselves, we also see that r squared value of 0.99. R can be between -1 and 1. The closer it is to 1 means there is a strong positive relationship between our x and our y values. The closer it is to -1 means strong negative between x and y. In this case, it's strong positive because, as we can see from our table, as our x values increase, so do our y values, and they increase at a strong rate. So that's what that value means. So we now have our equation right here. We can make a prediction for the number of bald eagle pairs in 2023. Well, 1963 is how many years? I guess 2023 is how many years from 1963? The answer there is 60. So again, it's like we're trying to use the information we have to make a prediction based on how many pairs of bald eagles there are going to be if our table value went all the way up to 60. So all I'm going to do is I'm going to take that equation and I am going to plug in 60 for my x. 397.53 times 1.08 to the, to the 60th power gives us what looks to be a really big number, but it looks like it should match. So we get 40,252.72. 40,252, I believe. 0.72. So based on our model, we are predicting that there are going to be 40,252.72 pairs of bald eagles. Again, you can have 0.72 of a pair, so we're going to round this up because 0.7 is closer to 1 than it is to 0. So our prediction is 252 pairs of bald eagles. All right, so that is essentially how exponential regression is going to work. We're going to use our calculators. We are going to plug in our table values, the data we were given, and then we're essentially going to type this equation right here to tell our calculator, hey, take those values and write me an equation. Again, they will give us A values and B values, and then we're going to use them to plug in to get our model. Now, the one thing that might change is these values right here. Your table at the top could say x1 and y1. It could say x2 and y2. It kind of depends on how many tables you have. So for example, I've got a third table in here. If you notice at the top, it starts with x3 and y3. All right, so now what we're going to do is we are also going to take a look at an example for a log regression. Log regression is going to be very similar. We take the table of values we are given. We are going to plug into our calculator or Desmos, and we are going to create a table. Then we are going to write our regression equation, which is right here, to tell our calculator, hey, give us an equation that models the data. Now this equation is a little bit strange. We have y1 tilde a plus b times the natural log of x1. Our y1 and x1 again could change depending on what our table values say. We are going to actually give you these regression equations on your assessment, so it should make it a little bit easier for us. However, we should do our best to try to make sure we are comfortable and we remember them. So this example says, given the data, write a logarithmic regression model, then estimate the height when the tree is 9 years old. So what it looks like is we have the height of a tree and then the age of the tree. So I'm going to take these values. I'm going to create a table and plug into Desmos, click my magnifying glass, and we can see our data. So we should be able to tell that the data kind of goes up in curves to the side. That is pretty logarithmic, if you ask me. Now what we need to do is we need to tell our calculators, hey, take this data and give me a log equation. So what I'm going to do is I'm going to type in my regression equation, which is going to be y3 tilde a plus b times the natural log of x3. Now, once again, we're going to click that log mode button, and we can see that we have our a and our b values, and then r squared listed as well. So again, r squared is essentially going to tell us, hey, the closer it is to 1, the better fit our model is. Our line here, our equation, is to the data we are given. 0.9875 is a very good fit, so it tells us that this is a pretty good representation of our data. So we get 3.32 as our a value. Plus our b value, which is 8.74 times the natural log of x. This is going to be our logarithmic regression model. And now all we need to do is estimate the height when the tree is 9 years old. So that's like if we had an extra position, in this table right here for an x value of 9. So I'm going to take my equation, and I am going to plug in 9 for x. So I have 3.32 plus 8.74 times the natural log of 9. So I get 22.52. And so what that tells us is we are predicting that at 9 years, the height of the tree is going to be 22.52. And I'm going to assume we are talking about feet here. Okay, so that's how regression models work. Essentially, we are taking our values, plugging them into a table, and then telling them what type of equation we want our calculator to use the data points to create. That is a regression model, and we use it to make predictions. We've done it previously with linear functions, quadratic functions, now exponentials and logs. We will continue with different polynomials and such as our year goes on. Okay, as always, thank you for listening. If you have any questions or concerns, please feel free to reach out.